Hey everyone, and welcome to The Explainer. Today, we're going to dig into one of the most powerful and, surprisingly simple ideas in all of AI, the decision tree. It's the kind of logic that powers everything from a medical diagnosis to figuring out which movie you're going to love next. And it all starts by just learning to ask the right questions. So it really all boils down to this. How in the world can a machine learn to make really smart decisions? Not by using some super convoluted formula, but just by asking a series of simple yes or no questions. That's the big idea we're going to unpack right now.
The best way to get a feel for a decision tree is to just see one do its thing. So before we get into the nitty-gritty of how it learns, let's watch a fully trained tree make a call. We're going to see the destination first, and then we'll explore the journey of how it got there.
All right, let's send a new piece of data down the path. It shows up right at the top, what we call the root node. The very first question it hits is x0 less than or equal to -12? Well, our data point's x0 is 15, so that's a big no. It gets sent down the right-hand path. Then it hits another decision node. Is x0 less than or equal to 9? And again, nope, that's a no. So it follows that final path, and it lands at its destination.
And there it is. Boom, the tree says our data point is red. Now, notice how we can trace that exact path. We know exactly why it made that decision. That's called interpretability, and it is a huge advantage. Unlike some of those complex black box models out there, a decision tree literally shows you its work, which is absolutely critical in fields like medicine or finance, where you really need to trust the why behind any decision. So that was the what. But the real mystery, the machine learning part of it all, is the how. How did the tree learn to ask those specific questions in that specific order to get it right? Now, it's easy to look at this and think, hey, that's just a bunch of if-else statements, like a simple flowchart. But here's the magic. A human programmer didn't sit down and write these rules. The algorithm itself acted like a detective, digging through all the data to find the absolute best, most revealing questions and the perfect thresholds to split on. That whole discovery process, that is the machine learning. To really get how it learns, you have to understand its number one goal, its obsession, really. Above all else, a decision tree is on a quest for something called purity. It wants to sort all that messy data into the cleanest, most uniform groups possible. This slide here shows you exactly what that purity looks like. So look at the split on the left. We start with a messy, mixed-up box, but after that one question, the two new boxes are much cleaner. You've got mostly red circles in one and mostly blue squares in the other. That is a good split. Now, look to the right. That split didn't really help, did it? The new boxes are still a chaotic mess. The algorithm is literally programmed to always hunt for splits that turn chaos into order, just like that one on the left. So to pull this off, the tree needs a way to score the messiness of any group. It uses a metric called Gini impurity. Honestly, just think of it as a chaos meter. A score of 0 is perfect order. Every single thing in the group is the same. A score of 0.5 is maximum chaos, a perfect 50-50 mix. Every single decision the tree makes is designed to do just one thing. Find the split that causes the biggest drop on this chaos meter. Okay, so the goal is to drive down that messiness score. But how does the tree actually figure out the best questions to ask at each step? Well, it uses a strategy that's called a greedy approach. And it's called greedy because the tree doesn't really plan ahead. At every single fork in the road, it looks at all of its options and it asks one simple question. Which split is going to give me the biggest immediate reward, the biggest drop in impurity right now? It just takes that best option, doesn't worry about the long term, and then moves on to the next step. And here's that greedy choice in action. So the tree tests out a few potential questions. As you can see on the chart, splitting by age gets a Gini score of 0.45. Not great. Splitting by x0 is better, down at 0.38. But asking loves soda? Wow, that gives a fantastic score of 0.21. That's the biggest, most immediate payoff. The greedy choice is crystal clear. It's going to make love soda the next question in the tree. So the tree locks in that winning loves soda question, and then for the new yes group and the new no group, it starts the entire process over again. It greedily searches for the next best question for each of those new groups. This repeating process, this recursion, is how the tree literally grows itself one perfect, greedy split at a time, branch by branch. So let's just quickly put the official names to what we've seen. The very start is the root node. Every question point is an internal node, and those final answers at the bottom, those are the leaf nodes. That's it. Pretty simple, right?
Now, as powerful and intuitive as this all is, decision trees do have one major weakness we need to talk about. It's a classic problem in machine learning called the overfitting trap. This quote just nails the problem perfectly. Because the tree is so greedy, if you let it, it'll just keep splitting and splitting until every single data point from its training data is perfectly sorted. It stops learning the general rules and it starts memorizing the individual examples, including all the random noise and weird outliers. And here's the difference. A good tree, it learns the general pattern. It's simpler, more elegant, and it does a great job on new data it's never seen before. But an overfit tree, oh man, it's incredibly complex and deep. It might be 100% accurate on the data it trained on, but it's brittle. It just fails miserably when it faces the real world. So how do we stop this thing from going wild? Well, we basically give it some rules. We can set a maximum depth so it just can't get too tall. We can tell it, hey, you need a minimum number of samples before you're even allowed to make a new split. Or we can let it grow fully and then prune it back, just like a gardener, snipping off the weakest branches that don't add much value. These rules are the key to building a tree that learns instead of just memorizes. But this is where the story gets really, really interesting. Because a single well-behaved decision tree isn't usually the final goal. It's actually a super powerful building block for something even better. So the key takeaway is that a single tree is awesome because it's transparent, we can understand it, but because of that greedy nature, it can be a little unstable. Sometimes, even small changes in the data can lead to a totally different looking tree. But here's the brilliant solution. What if, instead of relying on just one tree, we built a whole forest of them? We train hundreds of slightly different trees, each one on a random chunk of the data. So each tree is kind of an expert in its own little area. Then, to make a new prediction, we just let them all vote. This is called a random forest. And what happens is the individual mistakes of each tree get canceled out by the wisdom of the crowd, creating an incredibly robust and accurate model. And that leaves us with one final thought. The power of the decision tree isn't just for AI. It's really a blueprint for clear thinking. So think about it. What complex choices or problems in your own world could you solve if you just broke them down one simple, greedy question at a time?